Welcome to our design project demonstration video. We are Team Rockflow Sim from University of Maratua. Our project focuses on simulating and optimizing a crusher system using discrete element method, a modern computational approach to analyze material behavior and performance in engineering design. Crushers are essential in aggregate and mining industries, yet traditional methods of performance analysis rely heavily on physical testing, which is both costly and time-consuming. This led us to ask, can we use simulation to predict and optimize crusher performance before building physically on the site? That's where the discrete element method comes in. It allows us to visualize and quantify the interaction between thousands of particles, revealing detailed behavior within the crusher chamber.
Methodology overview. Our workflow began with data collection, then we did geometry design and initialization, simulation setup, parameter definition, and finally the process began with identifying the core problem, understanding the flow behavior of rocks within a crusher system. We first collected the essential parameters such as particle size distribution, material properties, and crusher geometry. These inputs were then used to create a component model that simulates rock particle interactions inside the crusher.
Using discrete element method simulations, we analyzed how rock particles collide, break, and move through the crushing chamber. Several design variations were tested to evaluate performance, energy efficiency, and output grain size distribution. The results from these simulations were then compared with experimental data to validate model accuracy. Based on these findings, the optimal design configuration was determined.
The simulation begins by defining the particle characteristics that represent rock behavior inside the crushing system. First, we set the particle shape parameters where each particle is modeled as a polyhedron to better represent the irregular geometry of natural rock fragments. Parameters such as aspect ratio, sphericity, and angularity define how rounded or elongated each particle is. These shape variations influence how particles move, collide, and break within the crusher chamber. Next, we define the particle size distribution. This step determines the range of rock sizes entering the system, from coarse particles to finer grains. This distribution curve is critical in replicating realistic feed conditions and predicting the output gradation accurately. The breakage parameters describes how rock fractures under stress. Here, we adjust values like toughness, fracture energy, and breakage probability, which control how easily particles split when subjected to compressive forces. Small changes in these parameters can significantly affect final particle size distribution and overall crushing efficiency. Following this, the crusher motion parameters are defined. For the crusher motion, periodic motion is applied to simulate the compressive action between fixed and moving jaws. The amplitude and frequency settings control how forcefully and how often the material is crushed during each cycle. Similarly, for the cone crusher, rotational motion is configured to replicate the oscillating cone movement that grinds the rock against the chamber wall. Parameters such as initial amplitude, rotational speed, and cycle duration are tuned to ensure stable operation and accurate particle flow behavior. Together, these parameters definitions allow the simulation to closely replicate real-world crushing dynamics, providing reliable insights into how design and operational changes affect system performance.
Here, you can see the dynamic particle behavior within the crushing chamber. The color variation represent contact forces and energy transfer between particles and the crusher surfaces. These level of variations is nearly impossible through experimental testing, but EDM allows us to observe the measure internal mechanism in real time. We also recorded particle velocity distribution and monitored the power consumptions under each simulation conditions to identify the most efficiency operational setup.
The simulation successfully predicted particle size behavior with acceptable accuracy. Two cone crusher models, 1321 and 1540, were evaluated to compare their performance. Results showed that the 1321 model produced fine aggregates, making it more economical and better suited for the existing low pressure configuration. Additionally, insights from the simulation allowed us to modify certain low pressure components, resulting in smoother particle flow and improved overall efficiency. These findings demonstrate the value of computational simulation in optimizing crusher design and predicting real-world performance with minimal physical testing. Using the discrete element method simulation, we can determine the power draw behavior of the cone crusher during operation. The model provides valuable insights into how power fluctuates over time for different crusher components, allowing us to analyze energy efficiency and machine performance under various conditions.
The discrete element method based analysis provided valuable insights into how small parameter changes can influence overall system efficiency. As seen in our simulations, variations in breakage parameters and sizing parameters results in noticeable differences in the particle size distribution, directly affecting output quality and energy efficiency. However, them simulations comes with a significant computational cost. As the system complexity increases, particularly when incorporating irregular particle shapes or more detailed contact models, the time required for computation rises substantially. Despite these challenges, the method remains a powerful tool for understanding granular material behavior in crushers. For future work, the integration of DEM, discrete element method, with computational fluid dynamics (CFD) is proposed to enable multi-phase modeling, allowing for more realistic simulation of particle-fluid interactions and improving predictive accuracy. For future work, this approach can be extended by incorporating additional processing systems such as screen, hydrocyclone, and high-pressure grinding units, enabling a more comprehensive simulation of the entire crushing and classification process. In conclusion, our design project successfully utilized the discrete element method to model, simulate, and optimize crusher performance. Through this approach, we identified optimal operating conditions that work efficiently while maintaining the required aggregate output. The findings provided valuable design recommendations for improving crusher systems. Moreover, the simulation framework can be extended to a wide range of processing industries in Sri Lanka, emphasizing the potential for expanding advanced technological applications in the country.